Good afternoon, everyone. So first of all, I would like to thank you for being here and also to the organizer to give me the opportunity of being here. I am Eleonora Bianchi and I work at the Arcetri Observatory in Florence. And today I will talk you about astrochemistry, focusing in particular on the organic molecules we observe in space. So in systems that will eventually evolve into ones similar to our solar system. Here is an overview of what I will cover in this presentation. So I will start with an introduction to astrochemistry, focusing on complex organic molecules in interstellar space and how they form. Then I will discuss the pre-stellar stage, where we already see chemical complexity at the very beginning of star formation. Then we will move into protostars, and I will explain how these forming stars act as molecular factories, with accretion streamers and shocks playing a key role in shaping their chemistry. Then I will show you some evidence that molecules can be at least partially inherited through these different evolutionary stages. And finally, I will give you a brief look at the future of astrochemistry, highlighting in particular how the next generation of radio telescopes will really revolutionize our understanding of astrochemistry. So what is astrochemistry? Is a truly interdisciplinary field that relies on the synergy between observations, chemistry, and astrochemical models. You can see the cats observer and the chemist. And in particular, observations allow us to detect and identify molecules in different astrophysical environments, while chemistry helps us to understand how these molecules form and evolve under the extreme condition of the interstellar space. And chemistry itself has two key components. One is laboratory experiment to study molecular formation and reactions, and the other is theory, so quantum chemistry calculations to predict reaction rates and molecular properties that are difficult to measure in the laboratory. Finally, astrochemical models, which are fed by reaction networks, allow us to reproduce the molecules that we observe and to test different scenarios. So, what are the fundamental elements that life is built from? We think that the building blocks of life are carbon, hydrogen, nitrogen, oxygen, and also in small quantities phosphorus and sulfur. And we know that hydrogen is the only one that formed during the Big Bang, while all the other elements are primarily produced in the interior of stars. So these elements are released into space through stellar winds and supernovae explosions, mixing into the protostellar medium, and they contribute to the formation of clouds, which eventually collapse again to create new stars and planetary systems. So the interstellar medium is made of recycled gas, which is enriching more and more in these elements. And in particular, I will focus on the formation of low mass protostars, means the systems that will originate a star similar to our sun and eventually to our solar system. And these are the main stages of the formation. So we begin with a cold and dense cloud of gas and dust, which is collapsing under its own gravity, and it's called the prestellar core. After tens of thousands of years, we have the formation of a protostar at the center of the cloud, and the material continue to accrete, forming a disk in the inner regions, while the angular momentum is removed from the system through the ejection of these collimating and high velocity jets and large scale outflows. So at this stage, the protostar is still deeply embedded in its natal envelope, and after about 1 million years, the envelope starts to dissipate, leaving behind a disk from which dust agglomerate to form a planetary system. So astrochemistry helps us to trace this evolution and help us to understand how much of the material is inherited from the early evolutionary stages to the planetary system. From a chemical perspective, we observe both simple and complex molecules through all the stages of star and planet formation. In particular, in the prestellar stage, molecules form in the ice mantles of dust grains, which we will see play a crucial role in forming the chemistry. And the species on the surfaces of the grains can hydrogenate, forming this first generation of complex molecules. Then, in the protostellar stage, as the protostar start to form, the temperature of the gas reaches about 100 Kelvin, and the icy dust grains mantles sublimate, releasing the molecules into the gas phase. The molecules can then further react into the gas phase, forming a second generation of more complex species. In addition, during the protostellar stage, we have the jets, protostellar jets, that can sputter and shatter the dust grains, further enriching the gas. Then, as the disk forms and cools, these species can be reincorporated into the ice and eventually also incorporated into the forming planets. And comets and meteorites, for example, which are the remnants of our solar system formation, provide us with valuable insights into the material that formed the solar system. To date, more than 330 molecules have been detected in space, and we are now able also to observe them in other galaxies. These molecules are detected through their rotational transitions into the gas phase mainly, and on the left you can see the number of molecules detected over time, along with some measured submillimeter and radio facilities that contributed to this discovery. So for example, you have a bump corresponding to the IRAM 30-meter telescope, or the Green Bank telescope, and also the Atacama Large Millimeter Array. And you see that I also put a star to update this graph to 2025, and we still are in really exponential growth. Some of these molecules are relatively complex, and we refer to them as interstellar complex organic molecules. So you have here some examples on the right. These are molecules containing 6 or more atoms, and they have carbon and typically include also oxygen and or nitrogen. And icons are of particular interest because of their prebiotic relevance, since they may be the building blocks for the formation of prebiotic species. For instance, you see in the graph formamide, which is related to nucleobases or amino acids, which are fundamental components of life. So we are particularly interested in studying these molecules. And how do these relatively complex species can form in the harsh condition of the interstellar medium? So you need to remember that temperatures can drop as low as 10 Kelvin, and the densest region have only typically 10 to the 6 particles per centimeter cube, while on Earth we have around 10 to the 19 particles. So this means basically that three-body reactions do not occur in space, which is why dust grains are so important, because they act as a third body for reactions, like for example the formation of H2, which is the most abundant molecule in the molecular gas. And you can see on the left a simulation of a surface of ice. You see the water molecules, which the cluster of water molecules which simulate the ice, and the two yellow little balls are the two hydrogen which form the H2 molecule and then released into the gas. And in general, there are two possible pathways to form complex molecules that you see summarized on the right. One pathway shown on the left includes a first step of hydrogenation on dust grain icy mantles, followed by a second step into the gas phase. The other possibility is that everything happens on the grains and the molecules are then released into the gas phase. So for some molecules, such as methanol, we know that the formation occurs on grains, but for other species, both pathways are possible and we still don't know which one predominates. So observationally, interstellar complex organic molecules have been observed since the early prestellar stage, and recent surveys in the Taurus and Perseus molecular clouds have shown that methanol is detected in 100% of the starless and prestellar core sample observed, while acetaldehyde is found in around 50 to 70% of the samples. And other complex organic molecules are detected in only a few cases. So, at least for methanol and acetaldehyde, they are common to several prestellar cores. An even more surprising discovery concerns complex carbon chains and rings. These were detected in the famous core TMC1, which is a well-studied core in the Taurus molecular cloud. And this was made possible by two surveys at radio wavelengths. One is called Gotham, using the Green Bank telescope, and the other is called Quixote with the Yebes 40-meter telescope. And these sensitive observations revealed previously unexplored chemistry, and they led to the detection of all these complex molecular species, such as benzonitrile, for example. I listed here some of the detected species. So this was an expected discovery, but subsequent studies have shown that TMC1 is not a unique source showing this type of chemistry, but there are also other sources which exhibit emission from these molecules. One example is the well-studied prestellar core L1544 that I show you here, where the IRAM 30-meter telescope had already detected interstellar complex organic molecules and small carbon chains at millimeter wavelengths. And on the left, you can see maps in particular of methanol and cyclic C3H2, which also reveal a different spatial distribution in this object. And additionally, observation with the Green Bank telescope in the X and the Ku band, so around 10 and 15 gigahertz, have detected emission from complex carbon-bearing species. And you can see here on the right the line-rich spectra obtained from these observations. As a first step, we focus on the emission of cyanopolyeins, which are this family of molecules characterized by one hydrogen atom, a chain of carbons, and a nitrogen. And in particular, we detected the strong emission lines from HC3N to HC9N, which was detected for the first time in this source. We used large velocity gradient analysis to fit all the species, and the results combined with the high spectral resolution provided by the Green Bank telescope, in fact, you can see that the line profiles are well resolved, revealed that the bulk of the emission originates from the outer layers of the core, particularly from this southern region, which is corresponding to the redshifted peak. And we know that the source is more exposed to the interstellar UV field since it's at the edge of a filament. And these findings are important because they suggest that this complex carbon chemistry is active in L1544 and may be driven by the UV radiation that liberates the carbon from the CO, making it available for the formation of carbon chains. In addition to our observations, we also revisited the formation pathways for the cyanopolyeins, and here I highlight the work of Lisa Gianni, who specifically revised the gas phase reaction networks for, in particular, HC5N. And it is important to note that only a small fraction of the reaction included in the chemical network databases have been so far studied experimentally or theoretically, because such studies are highly time consuming. So during her thesis, Lisa combined the theoretical calculations, laboratory experiments, and chemical modeling to reproduce the abundances observed in L1544. And we found that at low temperatures, these reactions labeled as 5 and 1 dominate the formation of HC5N. However, further work is needed to better understand the formation of more complex cyanopolyeins, such as, for example, HC7N and HC9N, and other more complex carbon-bearing species. So this was just a first step. Now we move on to the protostellar stage, where many interesting chemical processes take place. And in particular, as the temperature rises, the icy mantles of dust grains begin to sublimate, and all the complex molecules that formed in the previous stages are injected into the gas phase. Additionally, in this stage, there are many processes which contribute to further enrich the surrounding medium, triggering new reactions, for example, the outflow shocks. And I will particularly focus on the accretion streamers and accretion shocks, which have only been observed in the last few years. And I will show you also the chemical complexity observed at small spatial scales, particularly in the regions where the disk is forming. These early protostellar stages are of particular interest because we have mounting evidence that planet formation may start early when the disk is younger than 1 million years. This evidence is coming from observation with Sphere and ALMA, for example. Thanks to that, we start to see gaps and rings in gas and dust in very young protostellar disks. And despite the formation of planets is not the unique explanation of these substructures, it is one of the most plausible. And also another evidence comes to the fact that evolved class 2 disks seem not to be enough massive to explain the observed distribution of exoplanets. So, of course, if we think that planets can already start to form during the early protostellar stages, we want to investigate their chemical content as it represents the initial chemical budget of the forming planetary systems. In particular, I present you the FAUST large program, which is an ALMA large program dedicated to unveil the chemical composition of young solar-type protostars from envelope scales to the inner disk scales. And on the left, you can see a schematic representation of a protostellar structure, which highlight the envelope region and the centrifugal barrier region, which is the interface between the infalling envelope and the Keplerian disk. So FAUST is able to sample all the spatial scales until the 50 AU scales, which are the inner disk scales. And it includes 13 fields containing one or more protostellar sources. So many of the results I will present later come from this observational program. And on the right here, you can see the spectra observed with FAUST, which reveal significant chemical diversity among this sample. So from a chemical perspective, some protostellar sources exhibit a very rich chemistry with a lot of emission lines from these interstellar complex organic molecules. And these sources are called hot corinos due to their similarity to hot cores, which were discovered earlier. In particular, in the inner 100 astronomical unit around the protostar, the gas temperature reaches about 100 Kelvin, and at this temperature, complex molecules sublimate from icy dust grains into the gas phase. And on the right, you can see an example of hot corino with real observation of the protostar Aries 4A, along with a line-rich spectrum, which highlight the chemical complexity that you can have in these environments. So the astrochemical trail, we mentioned this because it was observed evidence of inheritance between the protostellar stage and the complex organic molecules observed in solar system comet. In particular, in these two plots, you see the abundance ratios measured in the young protostar IRA 16293, which is a famous protostar, the one observed, for example, in the PILS large program, and the comet 67P observed with Rosetta. And you can see that overall the abundance ratio show a good agreement within 1 order of magnitude. And on the plot on the right, you have the same considering multiple protostar at different evolutionary stages. So at least for some molecular species, it seems that there is a chemical inheritance from the protostellar stage until the formation of the solar system. When we observe protostellar sources, however, not all the systems have an hot corino, but we instead observe at least two different types of chemistry. Sometimes they can also coexist in the same source. So on the one hand, we have the so-called hot corino chemistry, rich in oxygen-bearing species, interstellar complex organic molecules, which is on the upper side, while The other situation is the warm carbon chain chemistry sources, where we observe hydrocarbons and carbon chains. So, one hypothesis for the origin of this difference is the different collapse time scale, which could favor chemical reaction starting either from CO or CH4 methane. So, in typical molecular cloud, all the carbon is in CO, is locked into CO, so you don't have enough free carbon to form carbon chains rings. However, if you have a fast collapse or the source is illuminated by a UV field which is extracting the carbon from CO through photodissociation, then you can have the formation of these carbon chains. We still need more observation to clarify the origin of this chemical diversity and to explore the complex carbon species in protostellar sources. So a first step has been done with these two surveys called Oranges and Peaches. So one is the two are performed with the ALMA telescope, one in the Orion molecular cloud and the second one in the Perseus molecular cloud. And they were meant to be compared, so they were planned using the same sensitivity and angular resolution, and they found that the number of hot Corinos in Orion is significantly lower than the number that we have in the Perseus molecular cloud. In one case, you have around 30% of the sources showing hot Corino chemistry. In the second one, you have more than 50%. So this led to the conclusion that probably the environment can affect the chemistry because Orion is an intermediate mass star-forming region in which you can have more star formation activity, so the gas may be warmer than Perseus, for instance, and this can cause a difference in the chemistry. However, regarding the warm carbon chain chemistry, the targeted molecules with ALMA, CCH, and the cyclic C3H2 didn't allow to properly study the warm carbon chain chemistry sources, so we still need longer chains and rings to explore this kind of chemistry. And I just want to mention regarding the feedback that the star formation can give to the environment, a very recent work. These are results from the FAUST large program and in particularly from Giovanni Sabatini, where in one of the sources included in FAUST, this is L1551 IRS5, we observe a tail of dust which is at the edge of the outflow cavity, which is here shown in red and blue. You see the two outflow lobes, and in color scale you see a tail, you see a circumbinary disk, the inner envelope, and a tail of dust at the edge of the cavity wall here. And observations show that in this cavity, dust grains are pretty large. So this suggests that the outflow can be not only important for the feedback on the gas, but also on grain growth, because they can lift possibly dust grains, even large dust grains, from the disk into the outflow. And I want to also mention accretion streamers, which are quite a new thing. So we know that at very early stages, the disk cannot be considered in isolation, but interacts a lot with the environment, and these accretion streamers were already predicted by theory of star formation, considering the collapse of a cloud with an initial velocity. But we started to observe them only in the last 5 years. And we know that these accretion streamers connect the envelope scale to the disk scale, so from 10,000 astronomical units to less than 100 astronomical unit. And they can have several effects on the star and planet formation. So first of all, they provide mass to the disk because the mass accretion rates measured are of the order of 10 to the minus 5, 10 to the minus 6 solar masses per year, so significantly high. They can also bring chemically fresh material from the envelope to the disk, and they can interact with the disk because we observe, for example, accretion shocks at the interface between the streamer and the disk. They were observed in a lot of molecular tracers, so gas, dust, isotopologues of CO, carbon chains, also deuterated molecules. We know that the accretion, they can basically bring material from the envelope to the disk at even higher accretion rate than those measured from the disk to the star in the near infrared, and they may be quite common because in a typical star forming region we measured, there was a first search which measured about 30% of incidence of accretion streamers. And you see on the left a few examples. So the first one is an observation in HC3N, and on the right you have the streamline model, which model the kinematics of the gas. To be sure that there is an accretion streamer, so we need to have infall into the protostar. And you see in the bottom panel streamers of dust observed at very small scales, so 10 astronomical units around a binary system, until the very large scales, so thousands of astronomical units. These are some results from the FAUST large programs in which we observed both accretion streamers and accretion shocks. So the first object is called VLA 16232417. It's a triple system composed by a binary system and a third companion. And you see that a huge accretion streamers was detected with SO on scales of hundreds of astronomical units. And we could measure for the first time here the temperature of the streamer thanks to the SO lines, which was around 30 Kelvin. And accretion rates of the order of 10 to the minus 7. While on the right, you have accretion shock revealed in HL tau thanks to the ALMA dot program. And this in particular was detected using SO, SO2 and other tracers at the interface between an accretion streamer and the disk. But the accretion streamers can also modify the chemistry. And here you have another nice example from FAUST in which a large-scale streamer was detected in the system IRS-63. You see on the right a beautiful image of the streamer detected in formaldehyde, and a zoom in of the dusty disk, which also presents some rings and gaps. And the interesting thing is that we measured, and you can see the maps on the left, super deuteration, so an enhancement of formaldehyde deuteration in the disk, which correspond to the region in which the streamer the gas from the streamer fall into the disk. So we think that there is an enhancement of the temperature, which is releasing the deuterated molecules into the gas phase. So another example of interaction of an accretion streamer with a disk is the system SVS13A, in which an accretion streamer was detected on large scales, and at the same time we observe several complex molecules at this scale, and in particular emission of formamide cannot be explained at this radii only by the thermal emission from the protostellar accretion. So we think that there is an accretion shock in this source, which is increasing the temperature and causing the release into the gas phase of these complex species. So regarding the last stage, protoplanetary disks, you have the molecules that were observed in a few large programs. The most famous are MAPS and the ALMA-DOT large program. And you can see a variety of molecular tracers. Here you have less species with respect to the protostellar stage, because the disks are colder, so many of the complex species are locked again in the ice. But still, if we consider the molecules present in disk, we have some evidence of inheritance. So here, for example, we compare the abundance of methanol and formaldehyde in different objects, and in the plot on the left, you can see this ratio for several objects, considering also class 2 disk, but considering disk average values. If you consider not the disk average value, but you consider the radial distribution, which is what is done on the right, you can see that in the inner region, you find higher values which are in agreement with the previous evolutionary stages and comets, while the outer disk presents lower values. And this is because in disks we have both thermal and non-thermal desorption processes. So we need to be careful to compare only the inner region, in which you have the release into the gas phase of the ice. And so this is what is comparable to the protostellar stage, for instance. So regarding the comparison with comets, I would like to also highlight this recent work by Manuela Lippi, in which for the first time she does a comparison with methanol and formaldehyde, considering not only few objects, but a statistical sample of 35 comets. And basically, she finds a good agreement also. So again, the ratio is in agreement with values in the inner disk regions, and this is where ice sublimate, and it can be an evidence of inheritance from the previous stages. But also this work highlight the different values measured for the comet 67P that we used to take as a reference, possibly because of the different technique used, which is the mass spectrometer, which was used during the Rosetta mission. But this highlight the importance of expanding the sample of both disks and comets for this kind of comparison to have significant results. So, few take-home messages. Interstellar complex organic molecules are formed since the early stages, so we see them from the pre-stellar stage to the protostellar and protoplanetary disk stages. In the protostellar stage, we observe chemical diversity, and also we observe molecular tracers in accretion and ejection processes. When we compare the planet-forming disks and solar system comets, we see some evidence of at least partial inheritance from the early evolutionary stages. And I want to highlight another time the importance of the synergy between astronomical observation and chemistry to interpret these results. So now a little bit of a perspective of the future, what we are missing now regarding astrochemistry. So one important thing to realize is that dust opacity is a huge problem in the submillimeter. So for example, on the left you have the system IRAS 4A, and you see that when you observe, it's a binary system composed by two objects, A1 and A2. And when you observe it with ALMA, you see complex molecules only in A2. You don't see any emission from A1. If you observe the exact same system with VLA at the radio wavelengths, then you see emission of methanol in the two protostars. So this means that in the submillimeter, all your molecular emission is obscured by the dust. Another important thing that we realized is that large molecules peak at low frequencies because the line frequency depends on the moment of inertia of the molecule. So this is a very simple simulation of two species, HC13N and HC11N, with exactly same physical conditions, so temperature, column density, and line width. And you can easily see that the peak of the emission is shifted at lower frequency. So this means that going at radio frequencies allow us to detect more complex species. And fortunately, in the very near future, we will have a next generation of radio telescopes. So in particular, the next generation VLA. We will have ALMA major upgrades with band 2, which will cover the wavelengths between 67 and 116 gigahertz. And we will have also the wideband sensitivity upgrade, which will allow to observe instantaneously up to 16 gigahertz bandwidth around. And also the square kilometer array observatory, which is in construction and should start to observe in 2029. And in particular, I am involved in the Cradle of Life science working group of this SKA telescope, and we are preparing the science for the SKA Observatory, and the Cradle of Life working group will focus on grain growth in disks, complex molecules in the planet-forming regions, and the origin of the solar system. So now there are two major activities, which are the science meeting, which will be in June in Germany, and the chapters for the updated science case for the new science book. So if you are interested in joining the science preparation for these new facilities, please do not hesitate to join the activities of the working group. So finally, a little bit of advertising. This is a project that will start in October, and it's called Astrochemical Study of Early Embedded Disks. The aim is to study the physical and chemical structure of this embedded disk, answering to the question of how much mass is available for planet formation, the chemical composition of young disks, and when and how grain growth start to form planetesimals. It will be in Arcetri, and it will be an interdisciplinary project combining machine learning and astrochemistry. So stay tuned, because there will be few positions that will open regarding this, and do not hesitate to ask me if you are possibly interested. Thanks a lot for listening, and I'm happy to take any question.